Hi. So as you can see on the screen, my name is Avishai Ish-Shalom. I'm an independent researcher and consultant. So if you have problems around, resilience, distributed applications, performance, whatever, come talk to me or don't, whatever you feel like. And I'm here today to talk to you about milliseconds, the thing that nobody cares about. Because, you come to someone who's like, okay, my app is like 20 milliseconds, and then you're like, oh, how about we shave 2 milliseconds off of it? And I'm like, why? So the question is, what is the real cost of a millisecond? And also, it depends where. That's very interesting. So anybody heard about this term, latency amplification? And anyone? Yeah, no? No one heard about this? So let's do a quick, kind of mental exercise. We have a system, and this system is composed of two services in the database, and we have, a request that goes in, and the load balancer has like a latency of 1 millisecond for this request, and service A has about 5 milliseconds for this request, and the database is like another 5 milliseconds, and then we have service B, which service A talks to because microservices, and that's another 5 milliseconds. So that adds up to a total of, we all know arithmetic, 16 milliseconds, right? No. We actually get to 740 milliseconds. Now that's a big difference, right? How did we get to 740 milliseconds from 16 milliseconds? And the answer is amplification. So what's going on? Service B, down at the stack, okay, answers in 5 milliseconds, but it has a queue, and this queue causes amplification of 200%. We're going to get into that in a bit. And then on top of that, the load balancer also has amplification. So that's another 200% on top of that, so already at 400%. Then, of course, service A, when it tried to talk to the load balancer, actually there was some network problem. It hit a timeout. That took about 300 milliseconds. Then it had to retry. That took another 20 milliseconds. And then, it also had to talk to the database. It also had its own amplification because of queuing. And then service A itself had another 200% amplification because of queuing. And also the load balancer had amplification, relatively small one, only 110%. But you get the point. All of this adds up one on top of another, and that's how we get to 740 milliseconds on total. Okay? So, yeah, oh shit. That's something we didn't expect. It's a huge problem. You actually see it in a lot of real production systems all over the place. And the thing is, all of those things we don't think about, and actually happen all the time, have very large penalties which compound. Okay? So this is why we're having this conversation. This is the motivation for this conversation. We need to understand latency amplification and how the system dynamics impact performance. So I'm going to start by talking about queue theory, because it's essential to understand what's going on in the system. I'm not going to go too deep into this. I have other talks that talk about queuing theory. If you're interested in that, you can go look for them on YouTube. So this is going to be a very, very fast crash course. Stay with me. So what is a queue? A queue is basically a service center. Think about database, CPU, disk, whatever you want, that handles some kind of requests. And in front of that service center, we have a buffer, somewhere where requests go into, and the wait for their turn to be processed. And we have work that is incoming at some, probability distribution, and the service center has its own probability distribution, for handling the requests, because, some requests are being handled, let's say, at 1 millisecond, some of them are larger, some of them are smaller, so they might take like 10 milliseconds and so on. You get the point. And the time that it takes to service a request actually is composed of two things. The time it actually took the service center to handle that request. Okay, let's say disk sick, or how much it took the web server to handle the request, and the time that the request waited in the queue to be serviced. Okay, two different times. So if you think about the supermarket, for example, it's basically the time that you waited in line to get to the checkout counter, and the time that you were actually serviced by the person at the checkout counter, 2 different times. So the problem with the queue is head-of-line blocking. What is head-of-line blocking? Again, think about supermarket. Maybe you have, just 1 chocolate bar, but there's someone in front of you with a whole cart full of stuff. Okay? So you actually are not going to take a lot of time at the checkout counter, but you're still going to wait 10 minutes until all the people in front of you are going to be done. Okay? So that's head-of-line blocking. You're being blocked by someone at the head of the line. Okay? We've all experienced this, at the bus stations, train stations, supermarkets, whatnot. This happens with computers all the time. It's a very basic thing that happens in queues. So 2 problems with this. One is that we're waiting because of something that is completely unrelated to us. Okay? That basically it's an interaction between different independent tasks. So that's the first problem. The second problem is that it means that we're being impacted by high percentile jobs. Okay, so remember, everything in life is like a distribution, and sometimes, just because of probability, some of those things are going to take a lot longer, some of those things are a lot bigger, and if they just happen to be in the front of the line, it's going to create a big queue, a big backlog. Okay, so that's a basic problem. So if you look at a simulation, okay, or actually like measure what's going on in the queue, and it's easier to see it in simulation because, actually it's hard to measure this like, at the microscopic level in real queues. So this is basically a simulation of a queue, and what you see at the bottom is the size of the queue in individual moments, and the red line here is the average size of the queue, or if you want, the latency amplification that you get. And what's interesting to see here is that the queue is mostly empty. Most of the time it's empty. But every once in a while, just because of probabilistic things, maybe you get someone with a big cart, you see a large buildup, a spike, a buildup of the queue that is very, very fast, and then takes a while to drain it, queue goes back to being empty, and that's the general behavior of queues. They're mostly empty, but they have load spikes. And when they have a spike, the queue builds up really fast, and it takes a while to drain them. And it's actually a very interesting exercise. I do it all the time in my life. When I go to like a cafe or a supermarket, I just observe the queue, just look what's going on, and you actually see this behavior all the time. So what is the overall impact of this? This is a mathematical model, a very simple one. But queue theory basically is a mathematical field that predicts what will happen to queues. So you can actually see this behavior, okay? It's a non-linear rise in latency and amplification related to the utilization of the service center. So if you have, let's say, a web server or an application server, and let's say it's like 70% loaded, you can see that as you approach 100% utilization, latency will rise really, really fast. It will eventually reach to infinity, which is basically an outage. Okay? So that has some very interesting ramifications. And of course, first ramification is that if you actually try to run services at very high utilization, you're going to have an outage. You're going to have very high latency. So you can't do that. You always have to have some kind of overcapacity if you want to have decent latency. So this formula before, is for average latency. What you don't see here is the relation to the variance of the, the latency of a service, because you never have all requests at the same latency. So there's a formula, of course, that also factors in the variance of the distribution. And I don't know if you can see it here, but as the variation becomes worse, you can see here that it goes with the square of the variation. So when you have more variance, when you have high variance, you're going to get more and more latency. okay? And that's very interesting because mostly people don't think about how wide the latency distribution is when they think about performance. It means that if you have a database and the average latency is very far off from the 99th percentile of latency, you're going to have more amplification, you're going to have more queuing. Okay? So you should actually care very, very much about the high percentiles of your services and of your databases. So remember when you have a blind blocking, tasks that should be independent actually impact each other. And this is something that's very important to understand because many times you're like checking out one transaction which was slow, like a slow query, for example, and you're like, why was this slow? And actually it was slow not because of this specific query, not because of this specific transaction, it was slow because of something completely different that is seemingly unrelated, but it was hogging the resources that you needed. So you actually wait for something else. And if you think about this from a system perspective, all the transactions that come into a single resource or a single system actually impact each other. We know this from real-life experience. And when you have high variance, this makes everything much, much worse. So one of the solutions is to split things to separate queues. For example, have multiple servers, have multiple databases, and so on. Yes, that does help. That does isolate the performance issues, but it's less efficient. So it basically costs more money. Okay? Lowers the utilization and so on. If you're interested in that, again, I would refer you to my lectures on queuing theory. So just an executive summary of queuing theory. High utilization usually means high latency. This is non-linear, so it will go up really, really fast. You know, just 2 minutes and you're already in an outage. High variance, again, high latency, and shared queues is nice if you want to get high throughput and lower latency, but you know it's going to cost you. And never, ever, ever you have unlimited queues. Why? What happens if you have an unlimited queue? Outage, out of memory, disk space fills up, you get the point, okay? And of course, very high latency. So don't do that. So now that we understand queuing theory, we can talk about amplification sources. Where does latency amplification come from? So first obvious reason, we talked about this, queuing. Thing about queues is they are everywhere. Even in places you didn't think that you have a queue. Most queues are implicit. They're not Kafka, they're not RabbitMQ, not that kind of stuff. Every socket is basically a queue. Every lock is basically a queue. Every load balancer has a queue. Every resource pool, like a database connection pool, has a queue. You get the point, okay? Event loops, also queues. Schedulers, queues, okay? You have queues everywhere. What's the problem with those implicit queues? Mostly they are unmonitored. You don't know that you have them, and you don't know how loaded they are and how much amplification they cause. Okay? Some of them you can monitor. You can add monitoring manually if you don't have it already. Think about Node.js event loop, for example. Some of them you can only infer from other metrics. And of course, if you have sudden overload, think about load spikes. Suddenly you have a lot of traffic coming. You're going to get amplification spike as well. Okay? So first thing to remember. Second, very common reason of amplification, timeouts. Now, timeouts is something that we have to have because, again, you know, the universe is not unlimited. Everything in computers is actually like discrete and limited. So if we have a distribution curve of latency, it can go into infinity. We have to cut it somewhere, which is why we have timeouts. We cannot wait forever. But if you actually look at developers' code and you look at the timeouts that people put, you open the code and you see a timeout of 10 seconds. Okay, where did 10 seconds come from? So anybody knows what's the average latency of a round trip in a single availability zone in Amazon? Anyone wants to take a guess? Sub-second, that's true. How much sub-second? 2 milliseconds? Sub-millisecond. Yeah, how much? About a quarter of a millisecond, more or less. Okay? So think about this. Within a single availability zone, does it make sense to have a timeout for connection, for example, of 10 seconds? If you haven't been able to connect in like 5 milliseconds, you're not connecting. That's not happening. Okay, and you see those bogus numbers all over the place, and they're default. Some of them are hard-coded for years, and they make no sense. I gave some examples here. So for example, Node.js library, default connection timeout for MySQL, 10 seconds. If you haven't connected to the database in 200 milliseconds, that's not happening. Okay? No point. So you can see all those numbers everywhere. And you know how I know that most of the numbers are bogus? Because they are a power of 10. If you see a number that's like round and nice, it's bogus numbers. Those numbers don't exist in nature. That's not how it works. So highly recommend to look at those things. But the thing is, if you have a long timeout, you're blocking resources. And you're causing other things to wait because of headline blocking. So you can see how this impacts everything. Retries. We haven't been able to do something, we have to try again. Every time we try again and again and again, that's more latency, more amplification. You get the point. How many retries? Sometimes you see infinite retries. You can see how that becomes a very big problem. And every retry has a timeout. So first retry, if there's a timeout of 100 milliseconds, that's 100 milliseconds, second retry, another 100 milliseconds, so on, so on, so on. Do they all have to have the same timeout? Does it make sense? Actually, if you think about it like this, many times it makes sense to try the first time with, let's say, a timeout of 10 milliseconds. If that didn't work, then you do another retry, and that one might have a 100 millisecond retry. Or the other way around, depending on the strategy that you need. But it often doesn't make sense to have the same timeout for multiple retries. And people don't think about this. And this is a great optimization that is very, very easy to do. Fork join. So this happens a lot in distributed systems. Solar, for example, do this. Elasticsearch does this, and many others. Basically, you ask multiple backends in parallel, and you have to wait for all of them to come back to actually give the answer. And what's the problem with this? If you have to wait for the slowest one, you're very likely to hit at least one high percentile. Okay? So that means overall performance is going to be pretty horrible. Okay? So this graph here denotes the probability of hitting at least one 95 percentile, 99 percentile, and 999 percentile. And you can see here that with a P95, the chances of me hitting P95, at least one P95, are almost 100% when I'm already at like 50 parallel jobs. Okay? This is why Hadoop, for example, has horrible performance, and same with Spark, and so on, so on, so on, because you have to wait for the last one. So there are some things that we can do about this, but this is like the overall problem. Now, you would think I'm not doing this, but if you have microservices, microservices is like fork join, but worse. Because you are actually calling all of them, you have to wait for the slowest one, and they all wait for each other. Microservices is the single worst performance killer there is. Now, of course, there are things we can do about this, because we need to work with microservices for other reasons, but we need to design for it, and we need to understand that there is a very big problem with this. So remember, when you're talking about microservices, it's like fork join, but also latency, all the latency penalties, all the amplifications compound. Okay? So what can we do about latency amplification? How can we prevent it? First thing we can do is to set proper timeouts. Okay? How do we set proper timeouts? I have news for you. We are engineers. We can measure. If you take the latency distribution, like you actually get a histogram of your latency for a service, you can see where you can put the line on the histogram and actually see if I put a timeout of 200 milliseconds, what percentage of requests will fail. Okay, so you can actually tune it, and this is tunable. It's a trade-off that you can do very easily once you get the histogram. And then you can decide on a proper timeout, and it will not be a round number. Okay? And you can compare it with the failure cost. What do I mean by that? So we have a cost for the happy flow. We also have a cost for failure. What is the cost of failure? It depends. It depends on the business. It depends on the alternative, because maybe we have some default value or cache we can use, but you can compare it and decide intelligently what to do. Also, timeouts don't have to be static. Almost always you go to open a code and you see like a hard-coded number for timeout. But if you think about this, timeouts should be dynamic because they should depend on the load of the system, the current speed, how much resources you have available, and so on, so on, so on. And it's not very hard to do. It can be as easy as keeping, let's say, the last 1,000 latency measurements, which you should already have anyway, because I'm assuming you have metrics in your code, and just taking a P99 of the last 5 minutes, and then just take the minimum of that and some hard-coded value. That is already so much better than static timeouts and super easy to do. Second thing is having a timeout budget. If you have a system, especially if it's a microservices system that has multiple layers, then actually you care about the overall timeout. You care about the timeout of the entire system, the entire request. You don't actually care about individual services. And if you have one service that takes, for whatever reason, longer, that means all the other services have less time to do their job. You can propagate its information, usually using headers or some other means of propagating context. And then you actually have an intelligent behavior where every service along the way can decide if it's actually worth doing the job that it has. If the budget has only 10 milliseconds left, actually you might want to feel that you want to terminate that request early because you don't have the time to do your job if it takes 20 milliseconds to do it. So you can save resources and improve latency at the same time. This is a great strategy, highly recommended. Parallel dispatch. So you remember fork join. Okay, if we do parallel dispatch, which means that we go to 2 backends that do the same job, and we wait for the fastest one. Okay, that means that we can reduce the latency by avoiding high percentile latency spikes. Okay, so yes, it's a trade-off because we're going to use twice as many resources, or we can use some calculation or optimizations of that sort, but we can reduce latency. This is a strategy that is being employed by all the big companies. For example, I don't know if you know, but Google uses this very heavily because they have to talk to a lot of shards of the search index. Second thing you can do is speculative execution. You can try to get data before you actually need it. You can do speculative retries and so on, so on, so on. This is basically branch prediction. Okay, the CPU already does this. Smarter retries. Okay, yes, maybe I have to retry, but there are better strategies than just doing a static retry. One example is a speculative retry. I have the first request, let's say it has a timeout of 100 milliseconds, and 20 milliseconds into that, before I fail the first request, I already do the second retry. Okay? So it's kind of like a compromise between retry and parallel dispatch. Okay? And you can tune it in various ways. The CLDB drivers, for example, already do this. And this, of course, means that either your requests are idempotent or the read-only, but you get the point. And if you're going to do some kind of retry, you need to have your APIs idempotent anyway. Second retry should not have the same timeout. Probably they should have a shorter timeout, and if you're using a timeout budget, then just subtract it from the budget. And you can use probabilistic retries. Okay? So what do I mean by that? If you know that 95% of your requests in the last minute failed and you needed to retry, maybe there's no point retrying. Maybe the service, the backend, is just hammered, it doesn't work, no point wasting more resources retrying something that doesn't work. And of course, capacity and latency management. If you remember from the slide about queuing amplification relates to utilization. So we have to manage the utilization in order to get proper latency. Again, I refer you to my talks about queuing theory, but the bottom line is you need to do some kind of load shedding. Load shedding, rate limiting, all that stuff. And if you have high variance services, you need higher utilization. So yeah, that's something that needs to be done. This is, by the way, what you see on the slide, this is a very large part of building high-performance services, just doing capacity management and latency management. Last thing is reducing variance. Variance, and I cannot stress this enough, variance is the backend engineer's worst enemy. It's the most common cause of bad performance because it increases queuing and it increases all the other amplification sources. So if you think about semantics of your services, so for example, queries, GraphQL, SQL, whatever it is, the more complex semantics you have, the more the variance of your services will grow. Okay, because you will have some queries that are very complicated and some queries that are very simple, and they cannot coincide in the same service. So if you have something like this, and you can actually look at the histogram, maybe you see multiple peaks in the histogram, you probably want to separate them to different services. And that in itself would improve your latency and utilization. Preemption is also a very good example of this. So event loops versus threads. They have very different behavior when it comes to quality of service and variance of performance variance. Garbage collection, all that stuff, again, raises your variance. So, to sum up, what is the cost of a millisecond? It's much, much higher than you think, especially if it's low in the stack. So, databases, usually they're the lowest part of the stack. Every millisecond at the bottom of the stack, which means at the database, especially the high percentiles, would cost you a lot because of the amplification. It can be even 100 times. Okay, so the cost of a millisecond can be 100 milliseconds at your app. So I personally would suggest that you get yourself a database that has a very good percentile curve. Wink, wink, CLDB is out there. You might want to go talk to them. And there's a number of other vendors that can help as well. So if you have more questions, you want to talk to me about that, I'm going to be here. And thank you very much.